And the final talk is by Chen, who's a postdoc at MIT with David Jerrison. And he's going to talk about landscape net, which is an application of landscape theory and machine learning for eigenvalues. Lee?
Okay, so thanks for the introduction. So today I'd like to introduce landscape net, which is a new frontier in this landscape theory. And it's a toy model that we built to use for eigenvalue counting. So this is a joint work with Wave 1 as well. Okay, so let me just give you an introduction for our experiment. The experiment setting is on L2. The square integrable functions on integer points from 1 to 1,000. And the Hamiltonian is the usual minus Laplace plus a potential with periodic boundary condition. And here, the potential is IID, identically independently distributed distributions for x on 1, 2, 3, all the way to 1,000. And we require a potential to be positive, although we don't require it to be bounded. So it could go off to infinity. And of course, the objective here is to approximate eigenvalue counting, so NVE. The way to do it is to construct a neural net architecture, and we use it to generalize box counting. So you might ask, why do we do that? Well, first of all, the original David Philoche-Maiboroda box counting gives upper bounds and lower bounds for the true eigenvalue counting already. See, that's denoted by NWE with a superscript. Here, W is the landscape potential. But not only so, this not only just an inequality, in fact, we have a really good prediction, as you have seen in the previous slides by Wei. Oh, by the way, can you guys see the bottom of the slides here?
The very bottom, the predicted eigenvalue count is cut off. I'm reading
okay.
top half of the letters.
Let me fix that. All right, sorry about that. But as I mentioned, it's better than just a inequality. In fact, you can do it as a regression model with 2 parameters. So here's C1, C2. Multiplied by the box counting, you get a predicted eigenvalue. But as you can maybe notice from this model, it's rather in some sense underfitting. It only has 2 parameters. So what we'd like to do is to push this frontier as far as possible to throw in machine learning, which has been really successful recently, and see how much better we can get it for the performance. Okay, so before I dive into all the details, let me just show you a prediction that we have used. So the graph that you're looking at is the eigenvalue counting by landscape net. The potential that we are using is a uniform potential on integers from 1 to 1,000. The potential is between 0 and 1. So on the horizontal axis, you're looking at the energy E. And on the vertical axis, you're looking at the number of eigenvalues below E. And I make a note that the vertical axis is not scaled. So whatever you see is whatever the actual eigenvalue count is. The blue curve is the true eigenvalue count, and the orange curve is what is predicted by the neural net. Okay, now quantitatively, we tested this neural net on the bottom 10% of all eigenvalues. So that is 100 eigenvalues out of 1,000. And we tested on 30 fresh, independent, unseen examples. So when you test it on this, you compute the difference between the prediction and the true eigenvalues. You take the square of that. So on average, that gets you 3. So what does 3 mean? It means if you look at the vertical errors in the previous graph, the maximum, on average, the squared is 3. Notice there's a square. It's just not the absolute difference. It's the squared. So in general, it's relatively small. Now, in terms of complexity, if you compare it to actual eigenvalue solver with SLEPC, so the actual solver takes about 0.0012 second per eigenvalue. The neural net takes about twice as much, but I think we can definitely scale this up better than eigenvalue counting by SLEPC. And it takes about 1 hour to train. When I say train, I mean on the bottom 10% of eigenvalues. So it's 100 out of 1,000 from 300 examples. Okay. Now, let me describe to you how this landscape neural net actually works. So this will be relatively, and I will represent this as a neural net layer. So let's, for the purpose of illustration, take energy to be 4, and on each box Q, you have length 2. So on the screen, you will see a landscape potential W, and it's given by this vector 652173 for illustration purpose. the first thing you do is you compute the difference, E minus W, and you get, well, 4 minus 6 minus 2, and so on and so forth. Next, you do box counting. So first you look at the first box, minus 2 and minus 1. You take the largest of these, which is minus 1. You move on to the next box. You take the largest of these is 3. Go to the next box. The largest of them is 1. So for each box, you get a number. After that, you apply the heavy side. So you take whatever number, if the number you get from the box is less than 0, you just put it, you just don't count it, it's 0. If it's greater than 0, you count as 1 box. At the end, you sum them up. So in this case, well, the box counting predicts there are 2 eigenvalues. But let's sort of view them in a slightly different way. So first of all, on each box, you give it a grade. In this case, it's a soup of E minus W on the box. After which, after you get this grade, you get the score. You have to determine which box has a passing score. And that's the activation. In this case, it's done by the heavy side. If it's below 0, it fails. If it's above 0, it passes, and it gets 1. At the end, you sum them up. Well, in this case, it's weighted sum, where all the weights are 1. So we generalize this. Well, instead of, we'll give it a more general grader. It gives a score to the boxes. And instead of using heavy side as the pass-fail, the activation, you can throw in more general objects. And you don't have to take the sum, you take a weighted sum. As a matter of fact, in a neural net, the last 2 things are even more generalized. Instead of just having activation and weights, we'll do many layers of weighted sum and activations. So the general picture looks like this. You start with your input, which is your landscape potential. Let's say it's W or V or W prime. At the end of the day, you want to get a number. And this number is your prediction for the eigenvalue count. So first thing you do is you give every box a score. You give them a grade, and that's denoted by F. But you don't have to give one grade only. You can give many copies of grades. Well, the next thing you do is generalize this sort of summation. You do many layers of weighted sum and activation. So the last 6 boxes, the red 6 boxes, you take the weighted sum and you apply an activation. You do this repeatedly for all these boxes, but you get many copies of the answer. Then you move on to the next level. So this mimics sort of box counting. At the end of the day, you will turn a column vector, which is your input, your potential, into a row vector. And you want to go from a row vector to a number. The simplest way to do it is just apply linear regressions. You apply linear regressions, and you apply activation. Activation introduces nonlinearity. At the end of the day, you will convert your input potential, landscape potential, to a number. And that is our prediction. So in terms of sizes of these objects, the grader, the scorer, has about 10,000 parameters. The weighted sums and activation 60,000, and the final linear regressions and activations about 3,000 parameters. So as you can see, it's relatively large compared to just 2 parameters in this case. Well, what I haven't told you is, well, what exactly is the grader? And to find the grader, we look for an ansatz. And in fact, what we'd like the grader to be is to be the integral of the true density. So if rho is the true density, the grader will look like the integral of the true density on a box. So, but obviously we don't have the true density. If we had the true density, much things would be easier. But in some sense, we can have a leading order approximation to it. In this case, we simply take the semi-classical expansion of rho. But instead of using the potential V, we use the potential W. So as you can see, in the leading order term is just a Weyl term. So the Weyl counting log, that's the first term. And the next term, next order term, you have something that looks like a function A times function B, but both of these functions depends locally or pointwise on your input. So A depends pointwise on V, W, derivative of W, and B depends pointwise on W. But notice this particular form, namely A depends on VW W prime, and B depends on the difference between E minus W. Same thing with the first Weyl term. It only depends pointwise on E minus W. So what do we do for F? We train the neural net to learn F. We give the neural net an ansatz F, which looks like the summation, so the weighted sum over a box of the multiplication of two functions, A and B. And A contains exactly VW prime, and B contains the difference between W and E. And here A and B are construct from layers of neural nets once again. And WX are the weights which the neural net will learn. So at the end of the day, if you put everything together, you just get this picture. And you start from your input, you grade it, and you apply nonlinear determination of whether the grade is good enough. At the end of the day, you get an output, and that is our prediction. So thank you.
Thank you very much, Lee. The floor is open again.
I have a question about the. So I didn't get what exactly the previous last slide. You have this A and B that you are that are constructed.
So if you
yeah, what did exactly depend on? They depend on what? So it means that.
Go ahead.
Yeah, it's, if you have like a domain, and then you're going to test several potentials, extract, and learn the actual eigenvalues. And these A and B, they are supposed to work on this domain for any potential. Is that what you?
Right, they're supposed to work on any potentials.
Okay, but for this domain, they depend on the domain that you are, right?
A and B depends on the domain. The A and Z depends on the 1000 domain.
Okay.
Is that what you're asking?
Yes, and they depend only on that. I mean the topology of you know, the relation between the.
So as a matter of fact, A and B only depends on the value of the functions. So it really doesn't matter what the domain is. You give it 3 values, it spits out another value. So in a sense, A and B, it depends on sort of 5 values, or in this case, 1, 2, 3, 4. It depends on 4 numbers, and it's matrix multiplication on R4 and with activation. So in a sense, if you use a domain that's 10,000 or 1,000,000, A and B will just depends on chunks of 4. And so A and B is like this. So let me go to the next slides. Oh, sorry. So A and B is a bit like this red object. It only has, depends on, you know, the 6 values, and it moves on to another 6.
So if I got it right, so your input, it's the landscape, right?
The input is, okay, let me be very clear. So the input that the neural net actually takes is the potential.
Is the potential.
The potential V, the landscape W, derivatives of W, and some combinations of these things. But depends on how you say the input, it could actually just be V, then you compute landscape, then you get all these things. But what I actually feed into this machine is V, W prime, some linear combinations of these.
Because you could actually, without structuring at all the way the neural network processes the information, you could imagine to give the potential and to let the network itself organize and ask to get the eigenvalues at the end. So do you think it would naturally create a structure where it computes the landscape first and then, I mean, is it the minimal way of storing the information?
Right, so let me give you a interesting experiment that we did, but I didn't write on the slide. So what happened is I give the neural net 2 input separately. The first one is V, the other one is W. And I asked the neural net with the same exact architecture to predict the first 20 eigenvalues. Now, if I give it a V compared to if I give it W, it does it 5 times worse. Yes, the neural net will pick up and will kind of adapt to the potential. But W is such more sensitive potential for the neural net to adapt to that it does so much better.
But was the training set V or training set or W training set?
So which one? The one that I just said?
You
Or?
use the exact same architecture, but how did you train that architecture?
So I take 100 copies of V, I take 100 copies of W, and I generate the first 20 eigenvalues from each, and I feed them independently to the neural net. So there's 2 copies of the neural net. The first copy trains on V, the second copy trains on W, but the architecture is the same.
The training set.
V, and you test one you trained on W with a new W, and the second works better.
Pardon me, what's?
You take a training set of 30 Vs, and then you test it on a 31st V, and then you take a training set of 30 Ws, test it on a 31st W, and the second works better.
That's right.
Got it.
To be clearer, you take 30 Vs and you train it on the Vs, and then you test it on the actual answer for the eigenvalue. How many eigenvalues are less than the 10th? What's the 10th eigenvalue? That's the question that you're asking.
Yeah, but
the training set is the V's or the W's. The outcome on which you're testing it is the count, the eigenvalue count.
As a function of a certain potential or a certain effective potential.
It's always this. Those are the same because you do the potential and it's the same eigenvalue count. The effective potentials associated with the same potential.
I think I understand. I understood better when Lee said it. So, I mean, your goal is to make something where you feed it either a V or a W, and it feeds you the counting function, right? It outputs the counting function.
Well, the goal is you give me a V and I give you the eigenvalue counting.
Right.
But before I feed the input V into the neural net, I do a pre-processing, so namely a compute W, a compute W prime, et cetera, and then I feed that additional information together with V, and all these bundle into the neural net as my input.
Okay. Are there any more pressing questions, or are we ready to close this session?
I won't ask it as a formal question, but I just wanted to say that it's very interesting, and it would be great to have a chance to discuss in more quantitative terms. I mean, what we actually can say mathematically, whatever the word mathematics means in this context, but what we can predict and on the basis of complexity and this sort of things. But let's discuss it off the grid.